Hello, everyone. Today we're going to talk about transfer learning and how it allows data scientists to stand on the shoulders of giants. Before we get started, I'm going to assume that you have a basic understanding of machine learning and of deep learning, as well as a basic understanding of neural networks. If you'd like a refresher on what neural networks are and how they work, I'd strongly recommend this resource from YouTube on a channel called 3 Blue 1 Brown. So what is transfer learning? Transfer learning is leveraging knowledge gained from training for one task to accomplish another task. What essentially it's doing is taking advantage of the common patterns and representations that are learned by previous models to tackle new domains and new problems without having to build the model from the ground up. As you can see in the picture down below, when you're training from scratch, you're taking your data set, you're learning all the features in that data set through full training, and then you're outputting your results, in this case, in a convolutional neural network for image classification. If you're taking advantage of transfer learning, on the other hand, you're taking your pre-trained model, applying it to a new data set for a new classification task. In this instance, instead of taking our data and trying to classify into a bunch of different classes, we're only looking to classify into cars or trucks. So why would you want to use transfer learning? Well, as you might imagine, it's a lot more time and compute efficiency efficient in training compared to fully training a model from scratch. Because you need a lot less compute power, you also need a lot less access to high performance computing resources such as Rivanna. So you could train models for using transfer learning with a smaller amount of compute, including smaller GPUs than you would necessarily need for fully training a model from scratch. Compute efficiency also decreases the training and fine-tuning cost. So full training for some large LLMs on the extreme end can be in the millions of dollars. You're thinking GPT-3 around $4.6 million, all the way up to GPT-4.0, which was around $100 million to train. I do recognize that the training costs for less complex models than these large LLMs have been decreasing over time, and they are continuing to go down as we are able to train models more and more efficiently. However, you still want to take advantage of all of the training that people have already invested their time into. It also requires a lot less data for full fine tuning than for full training. Useful in limited data environments, such as some healthcare use cases. For example, if you only have access to data from one doctor's office or one hospital or one hospital group for that matter, you may not have enough data to fully train a model from scratch for your particular use case, but you might have enough data to take advantage of some pre-trained models and then fine tune it for what you're trying to do. Can also be used for many different neural network types. You're not going to be just limited to using this for large language models or for image classification models like convolutional neural networks. You can also use it for recurrent neural networks and other neural network types as well. So what are some potential issues with transfer learning? Well, unfortunately, any bias in the pre-trained model is cascaded to your new model and use case. So if your model was trained on a really biased data set and it's learned representations that are not really representative of the world as a whole, but only that specific imbalanced data set, you are going to have some of that cascade through to your new task. You can mitigate this to an extent through fine tuning, but you really want to make sure that you're using high quality models if you're going to be using transfer learning. It also may not be appropriate when the new task is substantially different than anything done before or for what that model was specifically trained to do. For example, if you're taking a model that was trained for image classification and trying to make it do time series analysis, you might end up in a situation where you have negative learning or worse performance than if you had trained that kind of model from scratch, even if you have a limited data set. You might get better results if you trained a model from scratch compared to using an inappropriate model type. So speaking of that, it also may not be necessary if you have a large enough data set and no resource constraints. For example, if you're OpenAI or if you're Microsoft, you may have a budget that allows you to fully train a model from scratch and transfer learning is not necessary. You can also run into some issues of overfitting if your model that you're trying to use is too complex for the new task, which you can mitigate again with some careful selection of your pre-trained model. So how do you implement transfer learning? Well, it's pretty simple. The first thing you do is you choose a pre-trained model, usually one that's trained in a related or similar task to your intended use case. Then you test the performance of that model. In order to make it work, you may have to add a few trainable layers or some output layers to the model to make it adapt properly to the task you're trying to accomplish. And then finally, you'll unfreeze some or all of the layers of your pre-trained model to fine-tune it for your task. And there's a couple of different packages available in Python for transfer learning implementation, such as Keras, which is built off of TensorFlow, as well as PyTorch. So one example of transfer learning that we actually used in the MSDS program, my colleagues and I last semester in a deep learning class, leveraged transfer learning in order to classify X-ray images and to find chest diseases specifically in those X-rays. So we were able to leverage transfer learning and fine tuning for a number of different pre-trained model architectures and applied that to our X-ray data set. All of these model architectures were trained on ImageNet, which is a large data set of images that have nothing to do with X-rays. It's over 1 million images. So we took advantage of all of the learning from those models, and then we fine-tuned those models with our X-ray data set and got some really good results. So you can really take advantage of everything that people have done before you by using transfer learning. With that, I'm going to go ahead and pass it back to our professor, and we can move on to the next topic.